what's up, danger? Like, what's up, danger?
Good morning, everyone. Today I got another literature review video for y'all. It's going to be a huge video because I have 8 papers I want to get through today. So here they are. If you want to take a look at them, you could just screenshot this and click this DOI link. Each of these articles has this DOI link. If you click that, you'll go to the paper. Most of the time, papers are free. Sometimes they're behind some kind of like subscription-based paywall. But you know, take a look at Google Scholar, type this name in, you could probably find a free article PDF of this. So yeah, we're gonna go through them. I can't read all these articles word for word on one video. It's gonna be a super long video. So I'm just gonna skim through them, read the abstract, conclusion, maybe some stuff in the introduction, take a look at some images and some stuff in the methods section, and we're gonna try to learn something interesting together. And I'm gonna highlight some stuff that I think is important to me. So I hope you guys enjoy. We're gonna start off and go one by one. Here are all the articles, and I have all of the ones listed up here. Actually, I might be missing number 2. But we're going to start off with this one. Phase diagram determined lithium plating / stripping behaviors on lithophilic substrates. So I guess it's good always to start with the abstract. I got a little coffee here. Many lithophilic materials have been proposed as substrates to homogenize the lithium plating, but fundamental understandings are still lacking to the drastically different behaviors of lithium on them. Herein, we study the phase transition process of a series of lithophilic materials and the lithium plating / stripping behaviors on them. A close correlation was found between the binary phase diagrams and the lithium cycling behaviors. The substrate, such as silver and I think this is magnesium, that only form solid solutions with lithium, shows high structural stability during repeated alloying and dealloying because of the lithium removed porous particles can guide the lithium deposition and support the interface layer. In contrast, the materials such as gold, aluminum, zinc, silicon, and tin that form lithium intermetallic compounds become lithium saturated and cannot modulate the lithium plating thereafter, resulting in poor structural stability and cycling behavior. These findings provide important guidance for the rational selection and design of the substrate in the secondary metal batteries. So this last sentence is kind of the main reason I'm reading articles related to lithophilic materials. You could see over here, let's actually highlight this, boom. And let's highlight this as well. Here they have a couple of materials, and it seems like in this article, right after they say herein, where do they say herein? Herein we studied the phase transition process of several lithophilic materials. So I'm assuming the materials they explore are silver and magnesium and all of these ones here. Here they have a little picture, and then they show that their results or their experiment distinguishes between these materials. So let's take a look at this picture here. Lithium plating, lithium stripping, long cycling. Ag, silver, I'm assuming these little blue circles are silver. And then Au, this is gold. I'm assuming these little purple spheres are gold. And then here they write lithium, SEI, solid electrolyte interface. Lithium plating, right? Picture looks fairly similar, but then lithium stripping, we get this whole SEI, the green thing starts breaking down, everything looks kind of bad. Over here, it's just the silver spheres inside that look like they're breaking down. Long cycling, not too much difference between silver for lithium stripping and long cycling. But here you get a lot of destruction. So lithium gold alloys or lithium zinc, aluminum, tin, and silicon, I think. And lithium silver alloys or lithium magnesium. So from just this picture, it looks like silver and magnesium perform better in the sense that they don't exhibit this kind of breakdown of the SEI. So we're going to figure that out. Let's take a look at the introduction. Like I said, I can't read every word of this, so I'm just going to skim through. The introduction is normally broken down into a couple of paragraphs. You can see paragraph 1 here is super broad. They kind of try to introduce the subject to all audiences. So it says, rechargeable lithium metal batteries are regarded as one of the most promising energy storage devices due to the low redox potential and high specific capacity of their lithium anodes. However, due to the formation of lithium dendrites so here they just introduce why are they interested in this research. They talk about metal batteries, dendrites, and stuff like this, the SEI layer. Surface level kind of introduction. Maybe not surface level to a lot of people, but still surface level in the sense that they're not talking about exactly what they're doing yet. This is the first paragraph of the introduction. Second paragraph also kind of like segues slightly into the research that they're going to do. So they say application of lithium wetting, lithophilic materials, or lithium alloys as the current collector is an effective strategy to improve the cycling stability of lithium batteries. Cool. Let's move on to the other. Actually, here the alloys are also used as 3D lithophilic hosts to accommodate deposition of lithium reduced local current density. I'm just reading this little section here because I can see here they start a huge list of materials. So I wonder what that is. Many other non-metals can form alloys with lithium, including, I think this is silicon? Should be. Zinc, aluminum, magnesium, and boron. Have also been proposed to reduce the lithium nucleation polarization and to improve the lithium cycling stability. These investigations demonstrate the feasibility of the alloying strategy to improve the performances of the secondary lithium batteries. However, the lithium plating slash stripping behaviors are found highly dependent on the texture of the substrates. There are significant differences in the nucleation overpotential, alloying extent, and morphology of the deposited lithium when different materials are used as the lithium plating substrate. A closer look shows that silver is usually used as an interfacial modification material to improve the lithophilicity of the current collectors, such as copper and carbon, while gold is utilized as lithophilic seeds assembled inside the carbon sphere or buried below the porous current collector to guide the lithium deposition. Okay, we're kind of diverging from reading the whole introduction here, but I didn't want to highlight something interesting here. So it says there are significant differences in nucleation overpotential, alloying extent, and morphology of the deposited lithium when different materials are used as the lithium plating substrate. Boom. So I'm gonna highlight this because that is interesting. Like, is that true? It seems like it is. They add like some little references here, which are at the end of the article. But do they actually prove that in their research? So here we have a huge picture. Let's kind of read what this picture says here. XRD, I think this is X-ray diffraction patterns of the silver at copper and gold at copper substrates during initial lithium plating and stripping at the current density of 0.5 milliamp per centimeter squared and the corresponding potential profiles. So these are all XRD. I mean, I think this is XRDA and this is XRDB for the silver and for the gold. So what is this telling us? I'm not too sure yet. I'm not the best at reading XRD patterns or graphs. So let's just see what else they have. In the addition to the points marked on the potential profiles, the XRD patterns at the discharge 2 milliamp hour per centimeter squared state were added to highlight the difference between silver and gold substrates. The peak around 44 degrees originates from the copper foil. The peak around 44 degrees. So around here, this peak. There's not one here. So this peak here, I guess. All right, interesting. The lithium silver C, which is here. Oh, also A is linked to this, the voltage as a function of areal capacity plot. And the voltage as a function of areal capacity for the silver and for the gold. C and D over here are lithium silver and lithium gold binary phase diagrams. So this is alluding to like the title here, phase diagram determined. I'm honestly also a little unsure of how to read these phase diagrams. I mean, I've seen them for water and stuff like this, but not anything like lithium and gold. Drawn on the basis of the XRD indexing and reference 34. AG refers to the lithium AG solid solution phase with the same structure as the metallic silver. Okay, this is some interesting kind of research here. It looks like they started with an XRD pattern, which is an experiment that gives you these kind of like peaks at specific degrees. And these peaks are telling you that there's a specific material present in your material. Over here where there's no peaks at all these angles, there's nothing there, so like no data. But wherever you see a peak, depending on what angle that peak is at, it could tell you like whether a specific material is present or not. That's why they said this peak over here, this 44 degrees, is the peak for copper, because both of these, silver and gold, are placed on a copper current collector. So over here, I'm not sure why they don't go beyond to show you the 44 degrees. They stop at 42. Anyway, it doesn't matter. What they're saying is, using this reference 34, which you can find at the end of the article, they use these two graphs and then they kind of build up these phase diagrams here. These phase diagrams look like they have temperature on the y-axis and the concentration or ratio of lithium to this silver on the bottom. And there's some crazy stuff happening here. Honestly, I'm not too sure how to read this, but we're going to keep zooming through the article. So here is the rest of the introduction, right? The introduction has not ended here. The introduction ends. Ooh, this is a large introduction. Does the introduction end? Oh, it's just introduction, I guess. Is that true? Let me see here. Let me zoom out a bit. They don't even break this article down into an introduction. They just have one big chunk of text, which is not the best. Like, I'm not too used to reading articles like this, but it's okay. Whenever I see this word here, though, I know that they're talking about the article itself. So let's see this. Herein, we clarify the relationship between structural variation of the alloys and the lithium plating slash stripping behavior on these non-metal substrates on the basis of their binary phase diagrams. So these little phase diagrams are what they're going to use to kind of make some comparison. On the basis of their binary phase diagrams, these metals are classified into two categories, and a selection principle of the substrate material is proposed. This is interesting because they're talking about a selection principle. So they compare all these materials, right? They break them down into two categories. We're going to see what they are, and then they select a material. I'm assuming they select either the best material or the worst material for whatever their purpose is. But that's cool. That's interesting. That's like them using their research to do something with it. So I'm curious what that end result is. Actually, we already saw it at the top. We saw that silver and magnesium are better. They don't crack and stuff. And all the other ones, they start cracking. So that's a bit of a foreshadowing in the article. The metals such as silver and magnesium that can be lithiated to form infinite solid solutions can regulate the lithium deposition slash dissolution throughout the cycling. The slight structural variation of the solid solution during phase transition ensures the structural stability of the substrate during repeated alloying slash dealloying, while traces of the metal atoms in the newly deposited lithium keep their lithiophility and allure to the lithium deposition. In contrast, the nonmetals such as gold and zinc that form lithium saturated intermetallic compounds can only affect the lithium cycling at the early stage of lithium deposition and at the late stage of lithium dissolution. Interesting. So I'm going to highlight this as well because this is kind of explaining why they're different. This is also explaining why they're different, but since I have two highlighted things here, the stuff inside the stuff sandwiched between the two highlighted things is also pretty important. I just don't want to highlight the whole article. I want to highlight like key bits of kind of important info that I can jump back to after I read this article. Once covered with pure lithium, they lose their modulation to the lithium deposition. On the other hand, over-dissolution of the lithium from such metals may lead to the substrate crumbling. These findings are helpful in guiding the rational selection of the lithium deposition substrates and the design of the current collectors to meet multiple requirements of the secondary batteries. In view of the fact that gold and silver substrates have been extensively studied but exhibit distinct lithium plating slash stripping behaviors, They are considered as representatives of the substrate materials and are comprehensively investigated in this article. Really cool in this article. So they mainly focus on gold and silver because they're like the heavy hitters in this field. The silver and gold coated copper foils were prepared by chemical method by ion sputtering, noted as Ag at copper and Au at copper substrates, respectively. More details for the preparation of these substrates and optimization of the results, figures S1 and S2, can be found in the supporting information. So when they say S1 and S2, they mean the figures in this supporting information. So if you click this, it leads you to another paper, which is the supporting information of this paper. So sometimes they split up papers like this. They write the main paper here, and then there's a lot of like small things like experimental things that they don't really want to put in the paper because it's going to make it like 90 pages. So they put the main important stuff in the main paper, and then they create a secondary paper called supporting information where they put pictures like this and details on preparation and stuff like that. The X-ray diffraction and X-ray photoelectron spectroscopy, XPS, characterizations demonstrate the presence of metallic silver and gold on the substrate, figure S3. The sizes of Ag and Au particles are both around 50 nanometers on the copper foils, figure S4. And here we have another diagram. What is this? Energy as a function of coordinate. Interesting. Schematic structure of the slab model of lithium 3 silver and lithium 3 gold. I guess this is like the compound that forms after you start cycling, and like there's some kind of alloy formed between the lithium and the gold or silver. The structures of the atom sites of the bulk model are similar to that of the slab model. Okay, this is interesting, but I don't want to get too bogged down into this one article. I kind of just want to look. So it looks like they mainly focus on the gold and the silver, and then that's how they separate their categories. So they have the two big categories, one being silver, one being gold. In this article, it seems like the silver is actually performing better and the gold is performing worse. I'm remembering this because of this little picture here, right? We got silver. There's some cracking over here, but nothing crazy, nothing completely diabolical destruction of the SEI. The gold, however, breaks it down over here. And then within these two big categories, within the silver, they put magnesium, which behaves similar to the silver. So magnesium is in the good category. Gold over here, they place all these other alloys, and they say this isn't the bad. They cause this destruction here. So that's the main thing I want to focus on here. They do some other analysis here. So I'm assuming this is SEM and the XPS. No, EDS. So these little like speckled patterns here kind of show you where in the material there is gold and copper and stuff like this. Pretty cool, pretty interesting. But for now, I'm going to just zoom through. Here, I guess they show some battery cycling, charge and discharge behaviors. And here we have the classic battery plots. Coulombic efficiency as a function of cycle number. And we have voltage as a function of capacity. I guess this is the nucleation over potential here. Lithium plating / stripping potential profiles in the second and 50th cycles. Comparison of the Coulombic efficiency of the lithium copper cells using silver at copper and gold at copper, and copper substrates, and charge cutoff potentials of 0.1 volts, 2 volts at a current density of 0.5 milliamps per centimeter squared, and deposition capacity. Okay, very interesting because they have three types of. They created a lithium copper cell. And it looks like here this blue one is the lithium with bare copper at 0.1 volts. This yellow is the lithium with the copper with the gold nanoparticles on it. And this green is the lithium with the copper with the silver nanoparticles on it. So it seems like the copper, the bare copper, performs the worst. Then it seems like the gold performs a little bit. I mean, in this picture, C, the gold and silver actually perform roughly the same. They kind of they make it all the way to like the final cycles here. But in this picture, you can clearly see the green one, this little silver, makes it all the way to cycle 250, while the yellow one, this little gold, dies off at cycle like 150, which makes sense with the picture they said before. So, pretty interesting. I'm just going to note that down. I'm going to keep in my mind basically how I'm going to summarize this whole article is this picture here. I can jump back, I can kind of see these highlights, and I can look at this picture, and I can see that silver is actually better than gold, which is interesting because mainly in this field of lithophilic materials, gold and silver are two big heavy hitters, as they showed you in the article. So I think I've gotten what I want to get from this article. I'm going to dive back into it later if it's interesting. For example, what's interesting here is they have some energy as a function of coordinate. So over here, they do some kind of maybe simulation. I'm not too sure, but it's just interesting, right? All these little things here appear when you do some kind of like molecular dynamic simulations. I'm not too sure. But I don't want to read through this because it's the first article of this series. So I'm just going to zoom through and see if I'm missing anything else. And it looks like I'm not. And there's no conclusion here. Yeah, because it's just one chunk of text. There's no like categories broken down. So this is the article. First article, phase diagram. Interesting. Thank you very much, authors. I'm going to keep this noted, right? As you saw, I didn't get everything related to this article. I mean, the first thing in the title says phase diagram, and I'm not really sure how to read the phase diagrams here off the bat. So of course I'm missing something important from this article, but the main findings I've kind of internalized, and I can just jump back to this article if I have some kind of like curiosity or I want to study it a bit further. We're going to jump over to Article 2, which is over here, an interconnected silver-coated carbon cloth framework as a host to reduce lithium nucleation over potential for dendrite-free lithium metal anodes. So a lot of interesting words here. Nucleation over potential, very cool word. Let's take a look here. Abstract. Lithium metal is considered as a potential anode for lithium metal batteries, but its commercialization process is hindered by several problems, including uncontrollable lithium dendrite growth and large volume expansion, low utilization of lithium, and so on. To address these issues, in this work, lithophilic silver layers with 80 nanometer thickness are coated on the commercial carbon cloth, CC, using thermal evaporation method to regulate lithium growth during lithium plating process. We find that the uniformly distributed silver layers can successfully reduce lithium nucleation over potential, thus inducing the homogeneous deposition of lithium metal supported by density functional theory calculations. Nice. I'm going to highlight that right away. Density functional theory is a simulation technique, which is interesting, which I haven't read too much about, but it's cool that this paper is doing it, so I'm going to highlight that. Also, I'm going to highlight this, coated on carbon cloth using this method. Also, just big kind of explanation of what this article is doing. Benefited from the as prepared lithophilic silver layers, the CC/Ag/lithium anode, so a lithium with the carbon cloth with the silver nanoparticles anode is created with an ultra high aerial capacity of 16 milliamp hour per centimeter squared is achieved, adopting electrochemical deposition at 0.2 milliamp per centimeter squared without the formation of lithium dendrites, which is confirmed by continuous detection using visual discrimination and scanning electron microscope observations. As a result, a stable dendrite-free carbon cloth / silver nanoparticle / lithium anode. I don't know if it's silver nanoparticles. It says silver layer, so it might not be silver nanoparticles. My bad. Exhibits excellent electrochemical properties. And here are the properties. 1. The assembled CC/Ag/lithium symmetric cell maintains a stable voltage hysteresis within 25 millivolts after cycling 750 hours at a current density of 1 milliamp per centimeter squared. 2. The assembled CC/Ag/lithium hyphen lithium iron phosphate cell. So this is a full cell, which is different from the symmetric cell that they make here. So maybe I can actually highlight that here. This is a symmetric cell, and over here, this is a full cell, which is interesting. Not all articles make these two types of things, so it's cool that this one is comparing kind of both. Not comparing, but it's actually like fabricating and analyzing both of these cells, which is cool. Also demonstrates enhanced electrochemical behaviors in terms of rate performance and capacity retention. When coupled with a carbon/sulfur cathode, the CC/Ag/lithium anode also demonstrates excellent compatibility. The initial discharge capacity of the CC/Ag/lithium sulfur cell. So this is also interesting. Lithium sulfur cell. So they don't just make one full type cell. This lithium iron phosphate, this LiFePO4, is like a commercial lithium battery cathode. And this sulfur is kind of a new cathode that people are trying to explore. They actually may be included here. Keywords: lithium sulfur battery, lithium metal, anode, silver. All right, cool. The reversible capacity retains a value of 587 milliamp hours per gram after 400 cycles, corresponding to a capacity attenuation rate of 0.0. Okay, interesting. So very cool article. As I said before, this introduction, you can read through this and kind of see if it's interesting to you. In the past decades, rechargeable lithium ion batteries, right? They kind of introduced the general public to what this article is about. Each paragraph kind of slightly segues deeper into what the article is about. Here's the second paragraph sentence. Recently, researchers have turned to the investigation in the three-dimensional conductive framework / lithium metal composite anode and the development of artificial host. This host is believed to provide the space for lithium deposition. Okay, yada yada. We're gonna read through that at a later time. I kind of just want to get the main bulk of this. So here in this work, this is synonymous with herein. So this is interesting to me. This is how they segue right into the article. Lithiophilic silver layers with 80 nanometer thickness are coated on a commercial carbon cloth using thermal evaporation method to regulate lithium growth during a lithium plating process. We saw that in the abstract. We find that the uniformly distributed silver layers can successfully reduce lithium nucleation overpotential, thus inducing the homogeneous deposition of metal lithium, supported by DFT calculations. Benefited from the as-prepared lithophilic silver layers, the CCAG lithium anode with an ultra-high aero capacity. Okay, this looks like it's just kind of repeating what they said in the abstract. So I'm going to zoom through into the experimental section. Material preparation, symmetric cell and coulombic efficiency. Okay, this is interesting, but I'm not gonna read it too much. My main purpose of this video is to figure out what kind of materials are good as lithophilic materials. And it looks like this article is just using silver. So this is just giving me another data point that silver is a good material. As you saw in the first article, we saw that silver and gold and some other materials were explored, and they saw that silver was the best one. In this article, they're only using silver, and they're using it in a couple different battery structures. So it seems like silver is a good material to use for the purposes of reducing dendrite growth. So I'm going to zoom through, right? I think the main information that I got from this article is already in my brain, but like I said, the DFT calculations are interesting. So this is what DFT calculations look like, these little kind of lattices of molecules. Right here we got C/lithium, Ag/lithium. Let's read what this says. XRD patterns of CC and CCAG matrices. So these are the this is the XRD. You could see there's peaks over here. The y-axis is just intensity, like how big the peak is. And there's a big peak over here and over here. And then there's some smaller peaks here. And you can see they sometimes label what the smaller peaks are. And over here we got an angle. You could search up how XRD works. You basically shoot your sample with a bunch of like electrons or photons or something. X-ray, yeah, X-ray diffraction. So you shoot it with X-rays at a different angle. So 10 degrees, 20 degrees, 30, 40, whatever. And you get specific peaks over here, and these peaks can tell you what material is actually included in your sample. Interesting. The galvanostatic discharge profiles of the electrodes. So these are voltage as a function of area capacity. Interesting. And over here, we actually see a difference over potential. So this blue line dips right below this green line, which is very, very interesting. So I'm going to read that a bit later. Not too important to look at right now in this video. What's important to me is these DFT calculations of bonding energy of a lithium absorbed on C, graphitic carbon, and D, silver surface. So this over here is like carbon, right? Some kind of carbon structure. That C is all these blue dots are the carbon, and this little red dot in the middle is the lithium. So we can see E subscript B, the binding energy, is negative 1.7 electron volts. Meanwhile, over here we have a silver matrix, silver lattice. All these little green yellow dots are silver, and this red one in the middle, this red orange one, is lithium. We can see the binding energy is negative 2.23, which is lower. So what these DFT calculations are telling you is the binding energy is lower for a lithium ion, a lithium atom, whatever, in a silver matrix as opposed to a carbon matrix, graphitic carbon, whatever that is. So what that's telling you is if you have like some carbon over here and some silver over here, and you like rain down lithium ions, the lithium ions are going to get pulled more to the silver because they're more attracted to it because of the energy at play here. So that's pretty interesting. We're going to look at all this stuff here. So here they developed the full cell lithium with this lithium iron phosphate. Pretty interesting. They also developed the lithium sulfur battery, and then they do material characterization, DFT calculations. Ooh, some interesting pictures here. So this is what the carbon cloth looks like once you zoom in on it. It's like woven together, and they put the silver nanoparticles onto that. But I think we are done with this article. Here they got the battery tests. Very, very cool article. So I'm not going to look at this any deeper because this article, let's actually read the conclusion. In summary, we have coded, this is pretty much the same thing as the abstract. We have coated 80 nanometer thickness silver layer on the carbon cloth by thermal evaporation process. The lithophilic Ag layers successfully reduced the nucleation over potential of lithium, thus inducing homogeneous deposition of lithium, which has been confirmed by ICM images DFT calculations. All right, cool. This is a fantastic thing to highlight. The carbon cloth slash silver slash lithium anode with an ultra high aerial capacity of 60 milliamp hour per centimeter squared is achieved at 0.2 milliamp per centimeter squared, devoid of formation of lithium dendrites. As a result, compared with the CC slash lithium symmetric cell, CC slash AG slash Li symmetric cell exhibits a smaller hysteresis of voltage within 25 millivolts after 750 hours. This is also pretty good to know. Boom. In addition, the full cell also demonstrates improving cycle and rate performance. Furthermore, when the CC slash AG slash lithium is used as an anode for the lithium sulfur battery, the cell shows enhanced reaction kinetics and cycle stability. Cool. Boom. This work not only shows the potential for the CC slash AG slash lithium electrode to be a high performance anode, but also provides a wide range of strategies for the novelty advanced lithium metal anode. Amazing. Thank you very much for this article. It's fantastic. As you saw, I just zoomed through it. I didn't read too many words, but I got the essence of what this article is talking about. Now I have it locked into my memory just a little bit. And once I zoom in, see my highlighted parts, I can see like, okay, this is what the article was about. Then when I ask myself, okay, what did they do for the symmetric cell tests? What did they do for the full cell tests? How did they create the material? I can just quickly zoom and get the information that's needed. So that's cool. That's Article 2. Now we're moving on to Article 3. Article 3. Strategy utilizing lithophilic gradients for dendrite-free lithium metal batteries. I'm sure you could see kind of a pattern with how I found my articles here. Let's read the abstract as always. If you want, you can also see the keyword. These are kind of like good things to like narrow down what the niche of your research is. Abstract. Lithium metal batteries, LMBs, hold significant promise for next generation energy storage due to their high energy density. However, uncontrollable lithium dendrite growth and the formation of dead lithium at the anode separator interface hinder their practical application. To address these challenges, we develop a novel strategy using a vertically distributed lithophilic zinc oxide gradient on a 3D carbon cloth substrate, GZNO/CC, to regulate lithium deposition in a controlled bottom-up manner. Okay, this is a crazy sentence right here, and this is basically the entire article in one sentence. Very, very nice thing to put in the abstract. The gradient, this is why they put a G here. The gradient is zinc oxide structure lowers nucleation energy at the bottom, homogenizes lithium plus flux, and suppresses dendrite formation at the top. So it does a lot of things. It does three things here. COMSOL multiphysics simulations further confirm that the graphene zinc oxide carbon cloth framework effectively balances lithium ion concentration gradients, promoting uniform lithium deposition. Experimental results demonstrate that the gradient zinc oxide, I may have said graphene here because I'm kind of used to this GO, meaning graphene oxide. This gradient zinc oxide carbon cloth electrode exhibits an ultra-long cycle life exceeding 2,500 hours. That's crazy because the previous article, they ran their battery for 750 hours. This one was 2,500 hours. That's crazy. That's a long time. 2,500 hours. I think 1 year has 8,000 hours. Damn. So I just checked on Google. 2,500 hours is about 100 days. So they ran this battery for like a third of a year with low over potential, 4.3 millivolts at 1 milliamp per centimeter squared. In symmetric cells. So it's a symmetric cell that they cycled for 2,500 hours. In a full cell with a commercial lithium iron phosphate, so you see how this cathode is again used. The previous article also explored this. So most battery articles, they analyze a symmetric cell, which is basically like, imagine like the plus and minus side of the battery. In a symmetric cell, they have one material here and the same exact material here. So the battery is symmetric. In a standard battery that you have in your phone or in your like car or something like this, the plus and the minus are different materials. They're called the anode and the cathode. Anode for negative side, cathode for positive side most of the time. And a commercial cathode, so this means that it's a cathode that's used like everywhere in the market. A lot of people use it. This lithium iron phosphate is a very popular cathode that they use. So this is why you see it in this article and the previous article. And this is why that they use it here, because it's kind of interesting to compare it to like the industry standard here. The lithium slash gradient zinc oxide carbon cloth anode achieves a discharge capacity of 149 milliamp hour per gram and retains 90% capacity after 1,000 cycles. This study highlights the potential of investigating lithophilic gradient strategies with 3D frameworks to enable stable dendrite-free lithium metal anodes, paving the way for safer, more efficient, high-energy batteries. Great. Again, we got the introduction, lithium metal batteries, classic introduction to the field. Second paragraph, a series of approaches have been explored to solve lithium dendrites, including optimizing organic electrolyte additives, forming artificial SEI protective layers, modifying separator with porous media, developing solid-state electrolyte, and designing lithophilic substrates. So this is an interesting thing I'm going to highlight here because this problem that all these articles are discussing is the problem of lithium dendrites poking the battery and causing short circuits and explosions and stuff like this. So here they mention that other articles, right, they list them here, article 3, 11, 12, you can find all these at the bottom of this article. The field of science has explored other areas, other kind of strategies of solving this problem. And this one specifically is using these lithophilic substrates. So that's the thing I'm looking at here. But it's also interesting to see what other ideas or other niches of this specific battery research field are doing to solve the problem, right? You don't want to just get locked in on one solution, because at the end of the day, it could not work. Maybe this guy somewhere across the world is looking at electrolyte additives, optimizing organic electrolyte additives. And then they post an article and they say, hey, this electrolyte is super ubiquitous, everybody's using it, and it completely removes dendrites in all types of batteries. So then this lithophilic substrate solution is pretty much useless because somebody already found a cheaper alternative. So it's good to keep an eye on what the other solutions are. But at the same time, this article is talking about lithophilic substrates and they list 15 and 16. So if you're specifically interested in this solution, you could take a look at these two articles, 15 and 16, and it gives you a bit of like a pathway moving forward to read other articles and see what the hell's happening. Nice. So I'm not going to read this too much. I'm going to just zoom through. Okay, here they got an interesting little picture. I like looking at the pictures because to me a picture just jumps out at me. As you remember the first article, this picture here pretty much summarized the whole article. Silver good, gold not good. Amazing. This one here, I don't remember too many pictures from it because the whole thing was just talking about silver. Here, I think they also look at one material, which is this zinc oxide. But let's look at the pictures because they kind of use different materials here. Figure 1, the schematic diagram of the working principle of A, carbon cloth, B, zinc oxide / carbon cloth, and C, gradient zinc oxide / carbon cloth in lithium deposition. Let's take a look. A, we got the carbon cloth, so I'm assuming these little woven fibers are the carbon cloth, and we got the lithium plus, which are all these orange dots going into here. Tip deposition. I'm not sure what that means, but here we have an orange layer, which I'm assuming is, maybe this means top deposition, I'm not sure, or the tip of the carbon cloth. Anyway, it looks like these lithium ions have infiltrated the top surface of the carbon cloth and they just developed some kind of like a layer. Normally they call this the solid electrolyte interface because this carbon cloth is one side of the battery. Inside the battery there's the electrolyte and all of these lithium ions coat onto the carbon cloth and they create this electrolyte interface. Here you could see the dead lithium, which are these little spikes here. So not good. Carbon cloth, not good. Then we have B, zinc oxide, carbon cloth. So I'm assuming the zinc oxide, actually they do tell you here. Here's the legend. Carbon cloth are these little like gray kind of lines. The zinc oxide are these little green balls, the hairy ones. And this is deposited lithium. And then these little orange ones are just the lithium. So here we have B, the carbon cloth kind of like fabric with the zinc oxide inside of it, and we have deposition of lithium. We deposit it, and here you can see there's still dendrite growth, but there's no dead lithium. So dead lithium is when the dendrite gets so big, it kind of snaps off. You see this little piece over here that's snapped off. You don't want that because this lithium is now floating around in the battery, and it reduces the energy density of the battery. Like the battery cannot perform as well because some of the lithium is floating around in the battery and it's dead. It's not part of the chemical reactions. You also don't want dendrites, so you don't want these pokey things happening at the solid electrolyte interface because they are harmful to the battery. Not good. But let's take a look at C. Gradient zinc oxide. So what they mean by gradient is I'm assuming, you see how here they have green balls distributed everywhere evenly all over this carbon cloth. Here, I'm assuming this bottom layer has more, and I'm actually correct about this because here you have two of these green dots, and over here you just have one. So at this bottom layer over here, you have more zinc oxide. At this middle layer, you have slightly less, and at this top layer, you have the least amount. So this is what they mean by gradient. As you move through the carbon cloth, the amount of zinc oxide particles or nanoparticles, whatever kind of structure they're in, gets less. Then they show you a bottom-up deposition. So instead of the lithium kind of getting coated at the top, it looks like it slides into the carbon cloth and starts forming first at the bottom. And then it forms a kind of like layers all the way on top, and you don't get this jagged structure at the very top that you get in here and that you get in here. So that's very cool. Basically, this whole picture, they're showing you that this gradient works better than the non-gradient, and the zinc oxide works better than the no zinc oxide. Interesting. So I'm gonna just take a look at that. Like I said, I want to take a look at different materials, and since this article is only looking at zinc oxide, I think I've gotten the main essence of what this article is talking about. I think I'm gonna move on to the next one, but I'm just gonna sweep through and see what else they talk about because I remember they said something about density, some kind of COMSOL uh, thing, which I think is simulations, which are interesting to me. Synthesis of the LFP, lithium iron phosphate electrode. So this is how they create it. Material characterization. Here they use EDS, SEM, some other characterization techniques. Electrochemical measurements. In my previous video, I kind of read deeper into this because this is how they actually cycle the battery. This is how they create the battery and also how they cycle it. Ooh, okay, here, these graphs here, I think are the energy, the COMSOL stuff. Let's take a look. Let's take a look at this picture. I love looking at the pictures. B, so B over here. Schematic of oxygen plasma treatment. Huh. Oxygen plasma treatment. That is interesting. I might actually go up here to see where they talk about oxygen plasma. Because, okay. Oxygen plasma is interesting to me. So I'm gonna just highlight that real quick, but I'm not gonna read too much about it. It's just interesting. And yeah. Wetting behavior of water on carbon cloth of C, oxygen plasma treated sides, and D, oxygen plasma untreated. So wetting behavior. So this is a droplet of water placed onto the carbon cloth here. This is oxygen plasma treated, oxygen plasma untreated. And you can see the water droplet is like a bit more round over here. The contact angle is bigger. And over here, it is much more like flat, like it has dispersed through it. Okay, not too important for this video, but it's kind of interesting to see that they actually did this little kind of experiment here. E, cross-section SEM images of graphene, or sorry, gradient zinc oxide slash CC. So this is E. Where's E here? And this is the cross-section. So, okay, here you go. Maybe it's hard to see, but here they have FGH. Did they actually talk about that? F to H, enlarged view of the top, middle, and bottom. So this is the top, this is the middle, and this is the bottom. Very cool. This is how they show the gradient. So this here is a like image, a SEM image of this entire carbon cloth network, right? So this is the full image, and here they have a zoomed in view of this F. So you could see it's just these like fibers which are part of the carbon cloth. Over here in G, it's kind of the middle. You could see a little bit of these spiky things. These are the graphene, or sorry, I keep saying graphene. These are the zinc oxide particles. And then at the bottom, this H, you could see a lot of, so this is the gradient that's forming, which is actually crazy to see. This is like a visual proof of this gradient actually forming properly. So that's very cool. Thank you guys for showing that. It must have been crazy to actually get those images. But what I'm interested in is this bottom figure here. So part I corresponding to, so these are SEM images. I'm gonna just keep zooming through. This is another XRD pattern. And then K to L. So K to I, A, B, C, D, E, F, G, H, I, J, K, L. This is L. Simulations of lithium flux distribution in K, zinc oxide slash carbon cloth, and L, gradient zinc oxide slash carbon cloth framework. So these are simulations here, which I'm gonna highlight. And it looks like after 200 seconds, here there's a bunch of red, But here there is no red. So just a color map showing you that there's differences between just the zinc oxide and then the gradient version. Very cool. Again, I'm going to zoom through because this article, they only explore zinc oxide. But now that I'm saying that and I'm looking at this, here they have silver slash CC, CNT, MgO, this cobalt thing, and silicone and some other stuff. So they actually put quite a lot of stuff. Let's see. Cycling performance, comparison of symmetric cell performance with reported gradient designs. Ah, interesting. So here they actually compare it with other materials. And you can see voltage is a function of time. This work. Huh. Okay, maybe I should spend a bit more time reading this, but we're going to zoom through. Let's take a look. Some more plots here. Okay, let's check out the conclusion so we don't spend too much time on one article. We have 8 articles to get through, and this is the third one. Conclusion. In summary, to address the challenges of preferential deposition of lithium at the anode and separator interface and the generation of dead lithium, we propose a novel strategy using zinc oxide lithophilicity gradients to guide lithium metal deposition in a bottom-up pattern. The gradient distribution of the zinc oxide nucleation site effectively lowers the lithium nucleation energy at the bottom of the electrode, homogenizes the lithium plus ion flux, and suppresses dendrite growth near the separator. Additionally, the 3D carbon network reduces local current density, provides sufficient deposition space, and accommodates the significant volume changes of lithium metal. This 3D lithophilicity gradient design effectively mitigates the lithium ion concentration gradient along the vertical direction, achieving a uniform and safe bottom-up lithium deposition. Experimental results demonstrate that the gradient zinc oxide slash CC electrode exhibits excellent electrochemical properties. Okay, interesting. So what I did not see in this conclusion is the comparison they made with all these different materials. You can see these materials here. Actually, they show, for example, here capacity as a function of rate current. So they have a bunch of other materials and they label them here with different names and colors. And it's interesting because I'm assuming they're just pulling this out from some other work. Right? I haven't read anywhere here if they actually develop it. I think in this article they just developed this zinc oxide thing. So yeah, I'm gonna take a look at this paper on my own time. But what I'm going to remember from this is this gradient over here. That I think is super telltale of this research. This specifically right here, these little spiky things, and also this kind of simulation that they had here. So I'm going to take a look at that in my own time. But this is article 3 that covers this one, and this one. Now we can go to article 4, which is a mechanistic review. Let's see if that's true. A mechanistic review of lithophilic materials, resolving lithium dendrites and advancing lithium metal batteries. So for this article, what I wanted to show you guys is that it is a review. In the other ones, you may not see, it says article here. In this one, it says article here. And in this one, it says article recommendations. But in the fourth one, it does not say article. Oh, view article online. Anyway, what I want to tell you guys is this is a review, which is a bit different than an article. So in a review, most of the time, reviews don't do their own experiments. They read and collect a bunch of information from other articles posted online and then try to summarize it and show it to you. It's kind of like a trailer of a bunch of different articles. So this one is actually quite interesting. We're going to start off by reading the abstract here. A mechanistic review of lithophilic materials, resolving lithium dendrites and advancing lithium metal-based batteries. Over the past decades, there has been tremendous progress to overcome intrinsic issues of lithium metal batteries. LMBs. Indeed, the advanced designs of lithium Li hosts, protection layers, and solid electrolytes, SSEs, are widely utilized for high-performing lithium metal batteries to address the issues of unstable solid electrolyte interface and lithium dendrites. However, the poor lithophilicity exhibited by most of those designs cannot regulate the initial lithium nucleation, which leads to a non-uniform lithium deposition that inevitably causes dendrite growth. Recent years have seen a growth of investigations into regulating the nucleation over potential of lithium by enhancing lithophilicity. In particular, the utilization of lithophilic materials, which allows for the effective control of nucleation sites to stabilize lithium deposition, has emerged as an essential strategy to enhance lithophilicity in lithium metal batteries. Nevertheless, a comprehensive overview of lithophilic materials for advanced lithium metal batteries is still absent. Okay, so they're saying it's absent. I'm assuming they're going to be the ones to make it non-absent. In this review, we cover a wide range of lithophilic materials that are successfully implemented as a component for lithium hosts, as a protective layer for bulk lithium foils, and as an interface mediator between lithium and solid state electrolytes. We also present opportunities and prospects for future development of lithophilic materials for safe and practical lithium metal batteries. So this is an interesting article. As you can see, it's a bit longer, these 21 pages. The other one was 8 pages, this one was 8 pages, this one was 9 pages. So normally articles, they try to make them a bit shorter, like 10 pages. Maybe if it's a crazy article, they make it really long. And reviews are longer, so you could see 21 pages here. They also have a lot more references, so they have a lot more pages of references. So anyway, it's interesting, and I think I'm going to spend more time on this paper because they are actually comparing lithophilic materials. So let's check out the introduction. The introduction of commercial lithium-ion batteries has brought undeniable classic introduction. Some of the authors over here. I'm not going to look at the introduction too much, although it is very important. I kind of want to get the essence of what the article is talking about. Some more authors here, very cool. Let's take a look at this picture. So it says, a schematic summary outlining the use of lithophilic materials for the applications of lithium hosts, lithium metal coating, and solid state electrolyte. So we got polymer hosts, metal hosts, carbon hosts, lithium host construction, lithophilic materials. So one of them could be lithium host construction, lithium metal protective coatings. Here we have lithium foil, composite / non-metal coatings, metal / alloy coating. So this is, I think, what we've been looking at, some kind of coating onto the lithium foil. And then we got solid electrolyte interface mediator, oxide, sulfide, lithophilic interface. So maybe it's like a combination of these two. I'm actually not sure. Maybe a combination of all these three is what we've been looking at in the previous articles. So let's see. As I said, it's a review article. So normally there's no like materials and methods section. It goes from introduction straight to lithophilic materials as lithium host. So let's just read the sections here, like the kind of titles here. First, increasing lithophilicity in carbon hosts. So here we got a picture, kind of interesting picture. Carbon fibers, Ag nanoparticles, carbon fiber, carbon nanotube. Looks pretty interesting. Increasing lithophilicity in metal hosts. Increasing lithophilicity in polymer hosts. Lithophilic materials as protective layers for lithium metal. Metal-based lithophilic coatings. Aha! Check this out. An interesting table. Let's take a look at this table actually. Electrochemical performance of lithophilic host materials. Host type. 3 hollow carbon shells, carbon fibers, graphene matrix. Is there a carbon Is there copper cloth here? Copper, carbon. Okay. Lithiophilic materials, we got gold nanoparticles, silver nanoparticles, nitrogen doping, zinc oxide nanoparticles, oxygen, graphene, copper oxide, zinc oxide coating. So, okay, this is the stuff that we've been looking at here in the lithiophilic materials. This is the stuff I've been interested in. We got the gold and the silver and the zinc oxide. So the zinc oxide was this previous article we saw with the zinc oxide gradient. This second article just looked at silver, and this first article looked at silver, gold, and some other alloys here. So they include silver and gold here. They write the max current density and aero capacity in half cells. So here they write some numbers: max current density in overpotential and symmetric cells, cycle life of symmetric cell, and the reference. Interesting. So let's take a look at the gold nanoparticles. It actually doesn't include the cycle life. But let's take a look at the longest cycle life. So we got 1700 hours here. I think 1700 is the longest one for the zinc oxide nanoparticles. And if we look here, this one with the zinc oxide gradient lasted 2500 hours. Interesting. And here we got max current density. I think a higher current density is better in this case. So it's split up into milliamp per centimeter squared, milliamp hour per centimeter squared, and cycle. So the gold one here lasted 300 cycles. The silver one lasted 10 cycles. The zinc oxide lasted 200 cycles. Some interesting data here, and this is kind of what I've been trying to find here. What is the best material to use? So here they show you a bunch of materials. All of these references are included at the end of the article. You could see the articles and how they developed it and stuff like this. Like they may very well have read this article here and included it. However, I'm going to keep zooming through other forms of lithophilic coatings. So this is specifically in the section on metal-based lithophilic coatings. As you saw before, there was some polymer-related stuff and some other things like this. Let's see if there's something else that is interesting to look at. Another picture here, lithophilic materials for lithium/solid-state electrolyte interface. So I'm not looking at solid-state electrolyte, I'm looking at liquid electrolytes. So I may not look at this too deeply for now. Lithophilic interface for oxide solid state electrolytes. Here we have another table, and I'm assuming lithophilic coatings and their corresponding results for bulk lithium metal. Lithophilic materials, fabrication method, cathode type, C rate, long-term specific capacity, capacity retention. So this is another interesting table. Here we got silver and gold films/layers. And we have them made with the LFP cathode. And the C rate is the same, and the specific capacity is that. So it looks like gold and silver are the top always. I mean, maybe not. Here they have some other materials that do better, 600 cycles. It's hard to compare these because there's so many moving pieces, but just looking at the materials, gold and silver always appear. Lithophilic interfaces for sulfide solid-state electrolytes, summary and prospects. Okay, so some interesting stuff for sure. And the conclusion here is going to be long to read. So I'm just going to keep this in mind. I'm not going to look through all of this. My main interest was to see what they kind of showed, like what materials they showed. But to me, it looks like the same materials as we saw before. So gold, silver. Here we have nitrogen doping, which is interesting. Zinc oxide, which is also interesting. So to me, these ones jump out. The zinc oxide and the gold and silver. And then there's some other stuff here that we could look at, but mainly what I was looking at is single element materials. Gold, silver, zinc, tin, stuff like that. So that is article number 4. I think that's good enough. Little bit of a zoom through. I'm not going to read this whole review right now. We're going to move on to article number 5.